All right, so for a problem like this, hopefully you can pause and read it. All right, so we're going to start by drawing a sketch of the situation. Just going to draw Emily with her body at a window. She's throwing something, and it's at a 30-degree angle below the horizontal. Down to her friend on the ground. Okay, so in this triangle, we have to break the velocity vector into components. And if the velocity that she throws it is at 12 meters per second, that's always going to be the hypotenuse. And the resultant vector is the one we were given. The edges of the triangle are the components, and they have to fit tip to tail to meet the resultant vector. So we can see that our x component is going to be positive, and to find this is on the, I guess let's put the 30 degrees right there. That's going to be on our adjacent side. So from SOHCAHTOA, the one that goes with hypotenuse and adjacent is cosine. So we're going to have 12 cosine of 30 for our x component of the velocity, and our y component is on the opposite side of our angle, so that's going to be 12 sine of 30. And if you know your unit circle, sine of 30 is 1/2, so this is just going to be 6 meters per second. And I have to be very careful here because this velocity is going to be downwards, so -6 meters per second. And if you know your unit circle really well, then you know cosine of 30 is √3/2, so this is just going to be 6√3, and that's positive because it's pointing to the right. Now, what we're trying to do is figure out how far from the base. So right here we've got delta x. It's good to label your variables. Now let's think about what our knowns and unknowns are. A lot of times there's going to be some hidden knowns. So first of all, let's think about our delta y and delta x's. So our delta y is going to be the displacement of the ball in the y direction. That's downwards, so it's -4 meters. Delta x is what we are trying to solve for. We know the initial velocity in the x direction is 6√3. I'll go ahead and grab my calculator. 10.39 meters per second. And VIY is -6 meters per second. Acceleration in the x direction, assuming we're not taking into consideration any air resistance, that's always going to be 0. But in the y direction, acceleration in the y direction on Earth is -9.8 meters per second squared, as long as we're relatively close to the surface of Earth. All right. Time is a variable that we also don't know, so we're going to have to figure that one out. And let's think about our equations. Notice that there's no v finals here. So the equation we're going to want to use is the delta x equals vixt plus 1/2 axt squared. Ax is 0. So since we're trying to find delta x, we already know what Vix is. That just means t is a variable that we're going to have to figure out. So let's figure out t first, then we'll use that to figure out delta x. To figure out t, we're going to use the same equation that I just wrote, but we're going to switch it so that it's in the y direction. So VIYT plus 1/2 AYT squared. And some of you might see this as VIYT minus 1/2 GT squared. And that's because G is equal to positive 9.8. So the minus sign is already in there. If we do plus, then the negative sign is hidden, sort of, in the AY variable. I tend to like using this one. All right, so let's get rid of that. So our delta y is -4. Our initial y velocity is -6. 9.8 and a half is 4.9 t squared. this has a t squared and a t in it, which means it's a quadratic equation. So what I'm going to do, I'm going to rearrange these. We'll start with negative 4.9 t squared minus 6t, add the 4 to the other side, plus 4, and now we have everything set equal to 0. This is set up like a quadratic. By the way, let's just divide 1 everywhere so we can get rid of all of the negative signs. So 4.9 t squared plus 6t minus 4 equals 0. Then what you're going to want to do is plug this into your calculator or use the quadratic formula, negative b plus or minus b squared minus 4ac all over 2a. In this case, a is 4.9, the coefficient in front of the t squared. B is 6, the coefficient in front of the t. And c, just the constant at the end, negative 4. So you could go ahead and plug that in here. You will get 2 solutions, but because we're looking for time, you're going to want to figure out which time makes physical sense. That's always going to mean take the positive one. All right, so if you do graph this, what you're going to get, I did this a little bit earlier. You're going to get one solution there and one solution there. So obviously this is a negative time and this is a positive time. So this is the winner, and you should get about t equals 0.479 seconds. Now maybe this just looks awful and you want to do it a different way. In kinematics, there's often more than one correct approach to solving a kinematics problem, so I always let my students kind of guide what they're thinking about and kind of go from that angle. So there's always more than one way to go about it. We'll call this next one method 2. Now we're going to actually find v final, and then we're going to find t, and then we're going to find delta x. And I haven't really gone back and solved for delta x yet, but I'm going to show you 2 different ways to find the same time. The next method has an extra step, but as you'll see, it doesn't include any quadratics. So for many of you, that might be an easier way to go about it. So since we have acceleration, we're going to want to use the v final squared equation in the y direction. All right, v final y is our unknown. V initial is going to be negative 6 plus 2 times negative 9.8. Delta y is negative 4. Again, that's a really easy spot to make a mistake. So make sure that you're always remembering that delta x, delta y, those are displacements. So they're vectors, which means if an object is going down, that has to be negative. And we plug all these things in, you should get 114.4. However, remember that that's your v final squared. So to actually get the v final, you're going to want to square root that. When you take a square root, you always get plus or minus the answer. So we're going to get plus or minus 10.7 meters per second. Now, if we think about the problem, though, the final velocity in the y direction is going to be in the negative direction since the ball is falling down the entire time. So that means the v final we want to use is negative 10.7 meters per second. Now we have this equation, v final equals v initial plus acceleration times time. And this is the one that we're going to solve for time using t. I'm going to subtract v initial y to the other side. So I got v final minus v initial. And then I'm just going to have ayt left. So to get t by itself, we're going to divide by ay. Plugging those in, we've got negative 10.7 minus negative 6. Watch out for the signs. It's going to end up being negative 10.7 plus 6 divided by negative 9.8. And plugging that all in is going to give you 0.479 seconds. All right, so no matter what way, we can either add an extra unknown variable to the problem and find v final, then solve t, or you can solve it just with one equation, solve it with time using this equation, but you're going to end up having to solve a quadratic. I will say though here, this is a really always watch out. Whenever you take a square root, you have to think about whether it's positive or negative. Your calculator will always give you the positive answer. All right, so finally, t is 0.479. We can go back up here to our equation for delta x. Delta x, our initial x velocity was 6 root 3, which I guess I already calculated that to be 10.39. We're going to multiply that by our time, 0.479. And multiplying that all together, you get 4.98 meters. So that's how far Allison needs to be, technically, for her to catch it on the ground. If we want to account for her height, then our delta y will be a little bit shorter than 4, maybe like, well, actually, if she's a tall woman, then she might be 2 meters high, and then our delta y might be only -2. But anyway, usually we're just going to assume that it's going from wherever they say to the ground. So the height of Emily is 4 meters above the ground, which makes our delta y -4 meters to the ground. Hope that helped. I really like this problem because it really challenges you to think about vectors and really utilizing the equations.